All right, here's the last bit of notes for chapter 16 and for our equilibrium unit. So we're just looking at titration curves and interpreting like pH and titration curves. So a graph of pH of the titration mixture against the volume of added acid is called a titration curve or a pH curve. Okay, we talked about these last year. Okay, and so we should know most of these like points, like as far as like these here. But really, like, yeah, the pH values change as the nature of acids and bases, the properties of conjugate acid-base pairs, indicators, and stoichiometric relationships. As they change, they're going to change our pH. Okay, so kind of knowing some key words when it comes to these titration curves or pH curves. So titration error is any variance between the endpoint values and equivalence point values. Okay, and so that's, again, the endpoint refers to when that color actually changes. Okay, and so that's when we stop the titration. Okay, the equivalence point, it refers to the point in any chemical reaction where the chemical equivalent amounts of the reaction have been combined. So stoichiometric ratios from the reaction work out. So like in this case, the middle of this inflection curve is our equivalence point. In this case, with a strong base and a strong acid, that's going to be right around 7. Okay. So my endpoint that I then want to choose, I want to pick something that changes colors right around 7, such as bromothymol blue. Okay. So if I pick that, that's going to have my endpoint and equivalence point would be the same. If I picked a different color that changed colors down here, as you can kind of see, let me just say, down here, okay, if I picked something like methyl red that changes colors down here, then I'm going to have titration error because my equivalent point and my endpoint are not the same. Okay. Buffering is the property of some solutions or buffer solutions of resisting or counteracting any significant change in pH when an acid or base is added. And so like here we have a really strong base. We have the sodium hydroxide. We're adding hydrochloric acid to it. Okay. Right here, it's not changing very much though, even though we're adding this really strong acid. Okay. And so really what's happening is this is our buffering region. It's not going to change significantly until we reach that one extra drop, as you remember from last year. Then it's going to change pretty drastically. Okay, so the titration of a strong acid with a strong base always starts with a low pH, okay, and forms a solution with a pH around 7 at equivalent. So any kind of, whenever you get a strong acid, strong base, doesn't matter whether you start with the base or start with the acid, okay, you're going to have an equivalence point around 7. Okay, so that's something key to kind of remember for that one. Okay, indicators themselves are weak acids. Okay, so indicators are weak acids. That's why, like in your data booklet, if you look at indicators, you're actually given the Ka for the indicators. Okay, so in acid form, the indicator is one color. In conjugate base form, it's another color. An indicator is a conjugate weak acid, weak base pair formed when indicator dye dissolves in water. So you can write the general equation. So the indicator is here, H and IN just stand for indicator, okay, plus water, okay, and then the base would be one color. So in this case, it's litmus. So if we have red, litmus is red in acid, the base is blue, okay, and then we get conjugate acid. Okay, so when you titrate to an endpoint, you do not know the pH of the solution changes while you're adding the base or acid. So to determine the pH of the solution, with each additional volume added, you need a pH meter. So like you need to kind of record the pH to actually get what it shows up as the curve. When you do so, you can plot your titration curve. The graphs of titration curves can provide you information about the nature of your acid and your base. Okay, this is just kind of showing you again the indicator color, like as an acid or a base. Okay, indicators are quite general and given the pH range. The pH range is also relative to the Ka. So indicator is chosen to have an endpoint or a color change at the equivalence point, which we've talked about. And so if we kind of know our equivalence point, we can pick a good indicator. So like most of the time, like if we're trying to get that for strong acid, strong base, we're going to use something that changes around 7. So probably bromothymol blue or phenyl red, depending on what we have available. Okay, titration curves for weak acids and a strong base. The titration of a weak acid, it starts, again, it's a weak acid, so it's going to start up a little bit higher, around 3. Okay, then it has our buffering region. So because it starts up higher, our equivalence point is actually up higher. So it's around, in this case, right around 9, just above or just below 9. Okay, and so in this case, we would want to use an indicator that changes colors around there, so phenolphthalein. So this is the one we did last year with we used a weak acid, which we used acetic acid, and we did it with a strong base, and so we use phenolphthalein as our indicator. Okay, we can also go the other way where we use a weak base with a strong acid. It's going to pull the equivalence point down to like just above 5. Okay, so again, we want to find something that changes colors around that. Okay, sometimes it's helpful, like in these, it's showing like when we did ours last year, it was really hard. It went from like clear to all of a sudden it was purple. So a way to kind of help that is in your buffering region, if you add a little bit of another indicator such as methyl red, red will, like when you're first starting, it'll stay red. When it starts to turn yellow, you know you're getting really close. And then when it goes pink, then you got your phenolphthaleins changing colors. Okay, when you're titrating a weak acid with a weak base, really you don't ever do this because you don't get the steep curve. Whoops. All right. Yeah, you never use a weak acid with a weak base because like it doesn't give you a steep curve. So you avoid those titrations and always use either a strong acid with a strong or a weak base, or a weak base or weak acid with strong base, or strong and strong. Okay, if you do have to do one of these titrations, you have to use a pH meter, and it just kind of gives you this gradual line, but it gives you those different points. Okay, so this is kind of just showing all the different types of and like where the equivalence points are. Again, you don't have to know exactly where the equivalence points are, other than like strong acid, strong base is right around 7. Weak acid, strong base is going to be above 7. Strong acid, weak base is going to be below 7. So the pH of a solution at an equivalence point can be explained by figuring out the entities present at the time. So what we kind of did with earlier with the 5-step method, write out the entities, find your strongest acid and your strongest base, write out their equation, okay, and then you can find out what's actually happening here. What's our strong acid, strong base? And so just some different examples here of showing how to do that. Okay, titration curves for polyprotic acids and polyprotic bases. So again, polyprotic acids have more than one hydrogen. That's what makes them polyprotic. Okay, and then polyprotic bases can accept more than one hydrogen. So really what you're going to see here is they're going to have more than one equivalence point. You don't have to know where they are. You just have to kind of know what they look like. Like when we used to, or like when you take the diploma, they'd just give you an example and say like, which of the following shows a monoprotic acid with a polyprotic base, or things like that. And so you'd have to look at the way the curve looks. Okay, as soon as you see polyprotic, you know it has to have more than one kind of bump. And then you'd have to figure out which ones with, like, is a strong acid, in this case, strong acid with a weak base. And so whatever one you're starting with is where your pH will start. So we're starting with a weak base, we're adding a strong acid, it's going to have these 2 equivalence points. So yeah, these are some of the types of questions you get. Like, and again, the diploma is always multiple choice, so it just did show you a different example and you'd have to figure from that. So for this one, like an acetic acid sample is titrated with sodium hydroxide. So we have a weak acid and a strong base. So based on this, what's our equivalence point? So again, the equivalence point is halfway through this inflection point. So if we look here, so it starts just above 6, this inflection ends right around 10. So halfway between 6 and 10 is right around 8. So it might be a little bit above 8, but we'd say right around 8. Okay, choose an appropriate indicator. So you're just looking in your data booklet, okay, which indicator changes around 8. Okay, and like we said, it's just above 8, so I would probably use, in this case, phenolphthalein, because it changes at 8.2 and that it goes from colorless to pink. Okay, you might be able to, depending on like where it is, if it's a little below that, you might be able to use phenyl red, because it goes from yellow to red, right? So when it turns red, you know it's right around 8. Okay, and so there's sometimes can be more than one indicator that's used. The best one I would say for this is the phenolphthalein. Okay, write the Bronsted-Lowry equation for this reaction. Okay, and so for that, you're finding out your strongest acid and your strongest base. Your strongest acid, the only acid present, like if you write down all your entities, you have acetic acid, you have Na+, you have OH-, and you have water. So your strongest acid is acetic acid, your strongest base is OH. So it's going to be, I'll see if I can write it out here. Okay, so CH3, COOH, okay, plus our strong base, which is hydroxide, and again, we always have our double arrows here. Okay, again, this is going to give its H over to that, so we're going to get acetate, CH3, COO-, okay, plus H2O. Okay, it doesn't look great, but that's the kind of the general Bronsted-Lowry equation for this reaction. At the very beginning of titration, before the curve levels off, it rises. So it's saying here, like right at the start, it kind of rises, and then this levels off, and then it kind of goes up. Okay. Explain this rise in terms of entities present in the mixture before and after the beginning of titration. So the entities present at the start, you're going to have acetic acid. Okay, you'll also have a little bit of your indicator in there. And then as soon as you start adding your OH, okay, what's going to happen is, to start with, it's going to go up because it's going to turn into some of this. Okay, at this point, now when we add this, we can, depending on how much we're adding, it can go back and forth because we also have this entity present, so it can also go back to this. And so that's why we kind of level out and have this buffering region here. Okay, at the equivalence point, which ion is there more of? Hydronium or hydroxide, and how can you tell? Well, our equivalence point is up here around 8. Okay, and so if it's above 7, it's going to have more hydroxide. Okay, so buffer solutions. So a solution that contains a weak acid and a conjugate base mixture, or a weak base and its conjugate acid mixture, is called a buffer solution. Okay, so buffer solution resists change in pH when a moderate amount of an acid or base are added. Okay, so at the center of the buffering region, there's equal amounts of weak acid and conjugate base. Okay, and therefore, when you prepare a buffer, you want to ensure that these conditions exist. So really what you want is your weak acid and its conjugate base. So the equilibrium or reaction between ions in the solution shifts as predicted by Le Chatelier's principle and described below. So adding an acid to a buffer, So in this case, we have ethanoate or acetate ions react with hydronium ions in a solution. So this is our base. We're adding acid. This is its conjugate acid, and then water. So the position of the equilibrium shifts to the right when we start adding the acid, because we're adding this, so it wants the shift to kind of go the other way. The hydronium ions are removed by ethanoate from the sodium ethanoate component. And that's one thing to note is a lot of times, like you can't just add ions on their own. You have to add them with something. So lots of times we'll have sodium in there. Again, just a spectator ion doesn't really matter. But like, because when we add acid, it's producing a different type of acid, okay, and it's just shifting the equilibrium back and forth. Okay, if we add a base to a buffer, so hydroxide ions with hydronium, okay, then the hydroxide ions are removed, but they remove some of the hydronium as well and produce water. And so it stays neutral. Okay, and then this last one, the loss of hydronium ions pulls the acidic acid, and like it causes the other reaction to occur. So again, the pH is staying constant. So because we have all these entities, depending on what we're adding and what it's reacting with, it's going to cause the shift based on Le Chatelier's principle. Okay, buffer solutions have two important characteristics. So the pH of the solution, so it resists change, the pH of a moderate amount of acid or base is added. Okay, and then the buffer capacity is the amount of acid or base that can be added before a significant change occurs. The buffering capacity depends on the amount of acid conjugate base or base conjugate acid in the buffer solution. When the ratio of concentration of buffer components is close to 1, the buffer capacity has been reached. Okay, some common buffers. So the blood pH is buffered. This is kind of in the way, but it's by the hydrogen carbonate ion. So during strenuous activity, we build up some of our acid in the blood, okay, which then reacts with our bicarbonate or hydrogen carbonate to produce CO2 and water. Okay, hyperventilation. So as we're doing strenuous activity, it makes us breathe harder. So hyperventilation, we're breathing harder, causes the pH to increase because basically the OH is going to react with the bicarbonate to produce carbonate and water. But the pH needs to stay close to, it should be 7.2. And so like these two reactions are kind of going back and forth depending on what we're adding. So dihydrogen phosphate ions and hydrogen phosphate ions, again, are used to kind of help out with that. Okay, essential buffer, which operates to maintain stabilized pH in the internal fluid of living cells. Okay, cellular fluid has a pH range between 6.9 and 7.4. The buffering system has a pH of 7.2, so it kind of keeps the pH in that range there. All right, so that's the end of the notes. There really isn't much on the assignment on this stuff I just talked about. Okay, there would have been a couple of questions on your diploma. Okay, usually it just asks, like, if I'm making a buffer out of HCO3, you'd also have to add in like the conjugate base, so I'd have to add in some CO2. Or I could add, like if I'm making the buffer, I can add, like you just need the acid and the conjugate base, or the base and the conjugate acid to make a buffer.